Good afternoon, everyone. Thank you for coming. Today we have Axel Metz from h.a.l.m. So we're very lucky to have him here in Sweden for a few days. So we asked him to give two presentations. The first one today is on the roadmap, PV roadmap that in the last 8 years has become something quite reference to look on what is the direction. And tomorrow he will do on a inline inspection. So tomorrow it will be sitting in the same room in the same time. Axel did his Ph.D. in ISFH. He also led the PV groups there after Armin left. From 2002 to 2012, I think he was the R&D manager in SCHOTT Solar. And then he joined, I think, h.a.l.m. directly. And he's now the manager, one of the managers in h.a.l.m. So please welcome Axel for the great talk.
Okay. Thank you, Sif, for the nice introduction. It's my pleasure to be here. It's my first time at UNSW, so I'm a little bit excited as well, but I think we have an exciting topic today as well, and I think you're about the second group to see this presentation because this is very new results from the ITRPV roadmap. It's updated yearly, and just last week in Malaysia the new version was released, and I thought it might be very valuable to show you the latest results here. So let's dig into the material right away. And this is my outline, so I will start with a brief introduction, then we will do some cost and price considerations, and then I'll come to in more detail to the results down the value chain, wafer, cell, module and systems, and finally I finish with a summary and an outlook. So how does the ITRPV, the international roadmap for photovoltaics, more specifically crystalline silicon photovoltaics, work? So we have contributors from all around the world, 40 this year. The number increased, and these are manufacturers of PV cells and modules, equipment manufacturers, material manufacturers, but also research institutes. So we try to gather all the knowledge from the community and bring it together. And as I mentioned before, we stretch down from the whole value chain of crystalline silicon, starting from the silicon down to the system. And how does this thing work? So the participating companies, they get some questionnaires, and they fill out these questionnaires. Also this year UNSW participated, so thank you for that. I think mainly Bram did the work there. And then all the data is collected at VDMA, that's a German equipment manufacturers association. It's kind of an independent body because all the data is kept confidential from the single contributors. And then the data is processed, and only the median values are given, not the average values and not min-max values. So from the median values you cannot determine which company gave which input, and this is strictly required due to confidentiality reason, because we ask rather confidential information to the companies and to the contributors as well. So, and then the data is reviewed by the chairs from the different regions, EU, China, Taiwan, US. We have local chairs, and also the VDMA looks over the data, and then after the data is consolidated, it's published like it was last week in Malaysia, the next edition. So always around March we will do an update, because it's a living document, and I will show you why it has to be a living document. And here you can see two parameters we have been asking for since the last 8 years when this all started in Germany. So the first one is the silver amount used per cell. And you can see all the different colors represent the different editions of the roadmap, and all the values converge. So even, let's say, 8 years ago, the estimation for this year's silver consumption was quite good. So this prediction quality worked quite well. We attribute this because silver, it's a technology trend, and silver prices, they do not solely rely on the PV market, but they rely on the world market. Other way around, it's with the wafer thickness, which is basically driven by the polysilicon price. So there always the prediction was wafer must get thinner and thinner, but it never happened. So basically, due to strictly reducing silicon prices from the 2008-9 time frame to today, the wafers never got thinner, and therefore the predictions were wrong. But this was like an estimation of the industry, of the contributors, but they were wrong. So that just to let you know, that's not all the truth. What is shown here is just the picture under the circumstances given in the year the questions are asked. Because if silicon prices or something other changes very quickly, then the forecast changes as well. And this is attributed to because polysilicon demand and prices strongly depend on the PV market. So if there is a downturn in the PV, then there's an overcapacity, the prices fall down, and there is no requirement for thinner wafers so fast, because on the other hand, you will have yield issues with thinner wafers breaking in your production lines, and people need to avoid that. So, and also to give you an overview, so we increased the number of the contributors from 33 to 40, and also the questions we asked, we increased the number of shown figures. So we show not all the results, we only show selected results where we think the most interest is. I think we asked more than 80 or 90 questions, but we selected just the 60 most interesting ones. Also this has been growing over the years. Okay, let's come to some learning curve and cost considerations. So here you see the well-known PV learning curve, and each year we update this learning curve with the latest data point, always till the end of the year. And here you can see that's the latest data point. End of 2016, we passed the 300 gigawatt mark of installed capacity worldwide. So this is really a landmark. And in 2016, by itself, 75 gigawatt have been installed, mainly in China. I think 30 to 35 gigawatt, so close to half of this can be attributed to the installations in China. However, what you could also realize, PV has gotten much less expensive than it was a few years ago. There's an enormous price pressure on the manufacturers. And we are down to prices end of the last year to 37 US dollar cents per watt peak. And I looked up just last week the current data published by companies like Energy Trend. They're at 32 cents. So it's further reducing and putting further pressure on the manufacturers to save further costs. So if we draw a line through this double logarithmic graph, we can see from 1976, when the first data points were recorded, to 2016, so a stretch of 40 years, an average learning rate, it's wrong, not 21, but 22.5%. It had to be increased because recently, since 2011-12, we are below the learning curves, and these new points basically increase the learning rate for PV. But we'll come back to that at the end of the presentation and see where all this is coming from. Okay, let's have some look at the prices, how they have developed continuously. So here you see a graph for the silicon, wafer, cell and module prices, and you see there has been a steep decline from 2011-2012 time frame, but also recently there has been a significant reduction, and here you can see how this all splits up. And actually, while in, let's say, 2011, people were using, let's say, 0.32 US dollars per watt peak to manufacture their cell. Now it's only about a quarter of that. So in a time frame of just 6 years, the cell manufacturing cost, just the add-on cost, not including the wafer, have cut down by 3/4. So, and this one should always have in mind that crystalline silicon is a fast-moving technology and a fast-moving target also for other technologies who want to compete with crystalline silicon. The polysilicon could not keep up, so the share of polysilicon increased. And as I said before, there's a high pressure on the cell and module manufacturers due to this price decrease. Okay, let's leave the costs and the prices for now, and let's come to the technology part and start with the polysilicon. So here we see a graph about the polysilicon manufacturing technologies, and as you all know, most of the polysilicon is manufactured by the well-known Siemens process, but the fluidized bed reactor FBR will take some more market share because it has some further cost reduction potential, but it will not grow as fast as it was estimated before, because you need to do new investments for these capacities, and only with new capacities maybe FBR capacities will be built up. And in the last years, companies like GCL, Wacker, they build up new polysilicon plants basically based on the Siemens process, and so now they wait for the next investment cycle. Other technologies will probably in the time frame of the next 10 years range up to 10%. So this includes curveless wafers like epi-growth, lift-off, or UMG technologies. This is all covered by this gray portion of the bars in the upper 10%. So now let's move on to the wafer technology. So there we can see significant progress in the curve loss, especially for monocrystalline, which can be seen here with the blue triangles. This is due to the introduction of diamond wire sawing. Diamond wire sawing compared to slurry-based wire sawing, which is the, let's say, well-established technology, especially for monocrystalline works very well, and therefore has the capability using thinner wires, and also the diamonds are getting smaller, so the curve loss, so the silicon which is lost, is reduced. And this is important to get more out of the silicon which is crystallized. Basically, the alignment accuracy, which also shown here, stays constant. That the curve loss for the multi does not decrease the same way is that the diamond wire sawing, there are some challenges for that, especially the texturing of the multicrystalline wafers does not work because there's not enough saw damage from the diamond wire sawing. So the texturing method has to be altered, but I'll show some details about that later. Generally, also in wafering crystallization, the throughput still increase. One should see this, that this is only a relative throughput increase. So we put the 2016 values basically at 100%, then it's a spread from there. So all technologies will increase. But for example, the diamond wire sawing as of today is 2 times up to 3 times as fast as slurry-based wire sawing. So that's why people are moving to this new technology, because it has a much higher productivity. Also concerning the wafer growth equipment, the ingot masses as well for monocrystalline as for multicrystalline get bigger. You add more mass to the ingot also to add the productivity and reduce the costs. Okay, so here you see the clear picture, basically where there was a dramatic shift from slurry-based cutting of monosilicon to diamond wire. So within 2 years, basically this technology found their way into mass production and already today dominates by more than 75%. It is introduced into monocrystalline wafer cutting. And this is also one aspect why the mono wafer price approached the multi-wafer price, because there, through the more efficient cutting, you could produce the wafers less expensive and close the gap to multicrystalline, which is from the crystallization perspective more cost effective, but you need to cut wafers, and if that process is more expensive, then it adds to the wafer cost, and the gap between mono and multi closed down quite a bit. So then the manufacturers shifted more to mono, so the demand was higher. Now the gap got higher because there was not so big interest in multicrystalline wafers anymore, and so now the multi-wafer price decreased significantly. So there the gap opened up again. And here you can see the same graph for the multicrystalline, and here you see the problems with the introduction, also due to some crystal defects. The wires might break while cutting, so there are some other issues beside the texturing issue, what is slowing down the introduction of diamond wire. But we are quite confident that in the next years this will also increase. Okay, so here we come to the texturing process. So still from the 40 contributors we had this year, the majority thinks the standard acidic etching for multicrystalline will remain the mainstream technologies. Then we have what they call this wet nano texture, including the metal assisted texturing, and then also the reactive ion etching REI technology is to be seen, but there are environmental issue with it later too. So for the metal assisted texturing, you have to remove, for example, all the silver from your wafers, because silver is used as a metal to catalyze this etching process. And with the reactive ion etching, you have greenhouse gases like SF6 used in this process. So there you have to take good care of the gases and not let them go into the environment. So that's why we still think there's a but to REI, and it has to be seen how cost effective it will become and how you can deal with the environmental issues associated with that. Okay, then the wafer thickness trend I had been talking earlier on. So here we got an update for the next 10 years. Still, people think the wafers must get thinner, but what we can see for the first time, mono and multi-wafer thicknesses are splitting up, and this could be a real trend due to the diamond wire sawing, because the diamond wire sawing also enables to go to thinner wafers a little faster and give some more process security there. So therefore that could be a real trend, that the mono wafers might lead the wafer thickness reduction trend. What's shown down here, this is the thickness, what should be required for module technologies, alternative new module technologies which are not based on soldering anymore, because soldering with a temperature process put stress on the crystalline silicon wafers and cells. And there are other technologies which we will see are coming up, and they reduce the stress. And then this is thought from the module people, what could be the limit for the module technology, because it doesn't help if you make a nice thin cell, but you can't make a module out of it. So one should always think about that. And here you can again see the misleading predictions of the previous ITRPV roadmap. So basically they all were coming up, and still today the multicrystalline wafer thickness is at 180 micrometers. So nothing has changed due to the reduced, mainly due to the reduced polysilicon prices. Okay, so how do the wafer types share the market? So basically you can say around 65% is multicrystalline and the remaining 35% is monocrystalline. And there you have this old-fashioned standard multicrystalline, and here you have the what's so-called high performance with the small grains, where all the dislocations are basically collected in the grain boundary, and the material has largely reduced density of dislocations. This took over the lead as in the market share, but then P-type mono remains fairly constant, and then with new cell technologies, N-type mono wafers are expected to gain more market share. For example, with heterojunction cells or back contact cells, you need very long lifetimes and diffusion lengths. So that's where this material comes into play. So, but nevertheless, all the P-type material is also expected to stay dominant over the next decade. However, as I said before, the mono market share will increase. Then another issue which just came up, it was not on the radar last year, that the wafer manufacturers increased their wafer size. So just a little bit by going from 156, which is shown here by the blue bars, to 156.75. This seems to be only a minor change, but it adds more than 2% to the cell area, and you can improve your module power significantly by doing this simple change. And basically, you don't have to change your equipment, because previously the wafers have tolerances, let's say plus minus 1 millimeter, and the little addition in area is still within that tolerance. Of course, you have to be careful. You have to add to this wafer size also a little tolerance, and that's what happened. One manufacturer did not tell his automation supplier and was complaining about higher breakage rates. And then later they found out, they introduced larger wafers, but the equipment needed slight adjustment, but nobody took care of that. So it's very dangerous, these small increases, which are hard to see. So if you have two wafers, it's very hard to see the size difference. Also, this progresses in the monocrystalline, but also will be a trend in the multicrystalline, also resulting from reduced cutting losses to cut the bricks. So if you can make the kerf loss for the brick cutting smaller, you can use that as active wafer area. And why should you throw it away and you just utilize it? And that's the way to go. So mono will lead to this larger wafer size, but be aware, some manufacturers are thinking of even larger wafer sizes, like 161.75. So this will be the next step, and one manufacturer in Korea is already using this for their high efficiency solar cells. So you always have to be careful. In former times it was easy. You compare a 60 cell module, But now you have to ask, which wafer size are you using? Because people come up with new records, but if they forget to tell the wafer size, it's not worth anything. They might use the biggest wafers available on the market. So one needs to be a little bit careful about if records are published. Always it should be mentioned which wafer size they're using. Okay, this brings me to the cell part. And here we have the graphs on the silver again. So it's expected a nice linear reduction over the next 10 years. We have gotten already very far from more than 300 down to 90 milligrams in the past 8 years. So this is accounted by the better screen printing technologies, introduction of more bus bars. And so due to this fact, plating is same like wafer thickness reduction, always pushed further apart, because if you can do it with a standard screen printing technology by just using less silver and still be cost effective, then people don't dare about introducing a new technology which might introduce new risks to their manufacturing. So silver will stay the main material for the next 10 years, is expected by the roadmap. So this brings us to the throughput in cell manufacturing. Basically, here we looked at two different paths. So basically a progressive part where eventually within 10 years time frame, all the equipment will do 10,000 wafers per hour. So today you already have wet benches which can do close to 8,000 wafers per hour. So, and with a huge increase in capacity, you will see and the need for further cost reduction, you will see the need to go to higher throughput equipment, because throughput has been a major cost reduction factor in the past 10 years also. So when I was at SCHOTT, we started in 1998 with a 6 megawatt line, and just 10 years later, in 2008, we built our 60 megawatt line per single line. So in 10 years, tenfold the throughput. And while we cut the operators to 1/5, so basically we had a factor of 50 in productivity for the workers, and that was a big cost reduction factor, of course. But you will see also metallization equipment coming up to 5,000, 6,000 wafers, and also even the furnaces and the PECVD depositions will manage to go with higher throughput. So, but of course there's a challenge. If such a system breaks down, you have a huge loss in capacity, and you have to maintain your overall equipment efficiency. This means you have to improve your OEE. Okay, so how about the back-end testing, or the general inline monitoring of cell production? So of course very interesting for my company, since we sell inspection systems to the industry. So we see that AOI is widely established in the industry. Also the Chinese are going away from manual wafer optical inspection. They go to automated optical inspection, but also EL has found its way, electroluminescence has found its way into cell manufacturing, due to the fact that the module manufacturers ask for white cells, so cells without any visible EL defects. If that's for quality purposes or not, they don't care. They just want to have nice looking white cells, and because they want to sell white modules. And also infrared inspection by thermography will see a slight increase, but this is not so popular. Although I would say looking for hotspots is much more of a quality issue than EL. With EL you can detect cracks. That's also important, but what could be a safety issue for your modules is really the hotspot. If it develops and the module gets very hot, it can start to burn. So you want to avoid this and better do good sorting. Then here we have some other technologies like inline silicon nitride inspection. This also established that there is no increase seen. Then another technology for sheet resistance, emitter sheet resistance measurement. That will increase, and also slight increase we will see in the wafer incoming inspection, so that you monitor the wafer quality going into your cell manufacturing line. Okay, coming to the metallization technologies, here you clearly see for front and rear side that screen printing is thought to be the dominating technology. And as I mentioned before, plating is always postponed due to the massive cost reduction in screen printing technology. And yeah, so screen printing will remain the mainstream. Then further on with the metallization, so we have reached 50 micrometer finger width on the cell, which a few years ago was said to be impossible to do with screen printing in mass production. But due to the development of the pastes and the screens, the fingers got narrower and narrower. There's also competition for plating, where with plating you can do very fine fingers, but now the difference between the plated fingers and the screen printed fingers is not so big anymore. So there you come up with competition. And you go to more bus bars. If you have less conductivity in your narrow and narrow fingers, you move up to 4 bus bars or even 5 bus bars or bus bar less technologies. This interconnection technologies introduced by Meyer Burger and Schmid with the wires. It's coming. And it helps further to reduce the cost of silver. Basically, you shift the conductivity from the fingers to the bus bars. And that can be, and you shift it from silver to copper, because the bus bars are mainly made of copper. And then also a trend widely discussed, bifacial cells. So with the PERC cells coming up more and more, and other high efficiency structures, they are naturally bifacial cell structures, or they can easily be made to be bifacial. And companies are picking up on that, because you can have an extra energy production from the albedo, the light being reflected from the rear side of the module. And for example, Solar World, they have introduced this last year as a product, and they're selling it to the people without extra price. And therefore the people just get extra benefit if they have some reflective surface behind their modules. And if they don't lose anything. They didn't pay more in the beginning. So I think we will see this trend towards bifacial cells continue. Then let's say now coming to the physics, so improvement of the bulk, the front and the rear surface properties. Also there is the trend still for further improvement. One could see from 2010 to 2016, the average J-nut bulk was significantly reduced for multicrystalline, P-type multicrystalline, mainly due to this introduction of this high-performance multi-wafers. But it will continue for the mono, for the multi, for the mono, and also for the N-type mono, although there not such big progress can be made, because there you're already getting close to the limits of the silicon material. And I think also things like hydrogen passivation, the research you're doing here, that helps to progress on this route. So it's not all crystallization, but it's also in-process improvement of the silicon wafer material, what helps with a reduction of the bulk. recombination. But also, as we know, the surfaces must follow, and they will follow, and they will come down. They have come down significantly due to the introduction of PERC solar cells, but they will further reduce, as is shown here, to keep up with the bulk recombination improvements, because you have to balance it to have the best possible solar cell. So, and where is, for example, the front improvement also coming from, besides better passivation schemes? It's coming from the increase of the emitter sheet resistance, which is already up to 100 ohm per square. So that was, at my time at ISFH, that was the standard emitter sheet resistance which we would do for our high efficiency solar cells. And now this is in mass production and can be contacted with state-of-the-art screen printing paste. Impossible 5 years ago. So great improvement on the metal paste made this possible, that these emitters can be contacted, but there's still challenge. They have to try to contact 135 ohm per square centimeter wafer pretty soon. So, and for the emitter formation, I mean, there have been technologies like ion implant and selective emitter, but the homogeneous diffused emitter will remain mainstream there. So rear side passivation, also an easy picture. Aluminum oxide deposited by PCVD is the way the industry is going. Few are still trying ALD, and the silicon oxide nitrite will eventually disappear. And as you can see here nicely, there has been a huge drop due to the introduction of PERC in the rear side recombination, surface recombination. So that will take on and continue while these passivation layers are still being improved. Okay, now coming back to the overall picture, so how the different cell structures add up. So basically in 2017, we will see a market share of PERC around 20%. So one gets the imagination when you hear about PERC is being introduced, it should be above 50% already. But of course the people have to convert their lines, and there are huge manufacturing capacities out there, and this takes a while. So, but it will continue, and the BSF cells, standard BSF cells, will fade out. Then heterojunction will take part, and also maybe back contact cells will gain some market share, and eventually, and I know you're doing some excellent work here, silicon tandem, so maybe with perovskites or other semiconductors put in front of the silicon, that could be a technology to enhance beyond the limits of crystalline silicon, still use a silicon bottom cell. And then correspondingly, the people expect the PERC or the cell efficiencies to increase. So this is a very busy graph. At the lower end here you see BSF cells, multicrystalline BSF cells, and here with the circles you see the PERC cells. And basically the multicrystalline PERC outperform the monocrystalline BSF, and the monocrystalline P-type PERC cells, they outperform the N-type cells, because the material is getting better, and with the hydrogenation process there is not such a big difference between P and N-type anymore, and also the degradation issue is solved. So, and then we still have the heterojunction and the IBC-type cells, which have an inherent advantage over the PERC type, and must reach higher efficiencies like 26, because PERC is pushing up, and you can see PERC is expected to easily go up to 23, maybe even 24%. So there, the other concepts are getting pressure, and PERC is very close to common days manufacturing practice. So this brings me to the module part. So the front cover there a few years ago, it was just standard or structured glass, so it's all replaced by AR coated glass, and the lifetime of this AR coating still needs to improve. It's said to be at 10 years, but it needs to improve at least to 25 years because that's what the product warranty is. And also interconnection technologies for the cells. So of course you have the lead containing solder, but then you will hopefully have the introduction of lead-free soldering, and eventually, when going to thinner wafers, also the adhesive, because they offer a lower temperature perspective for interconnection. They could make their way into the industry. And for the cells, it will still be the ribbons, and then, as I said before, with this busbarless technologies, copper wires could be introduced, and then structured foils. They would be only used for back contact, and this back contact is expected to have a small market share. So that interconnect technology is expected to have a small market share. And shingled, which was a big hype to put, like in the race cars, put solar cells in shingles. Everybody is trying this out, but I think it will stay a niche technology because it's very difficult to match the different thermal expansion coefficients of the encapsulation and the silicon material. And basically, if you glue the cells like shingles on the roof to each other, you end up with a long stripe, let's say 1 meter of silicon, where it cannot move anywhere, and we have seen modules with lots of cracks. So this technology needs to be looked very careful if introduced in mass production. So the module cell to power ratio will increase above 100%. This will be done by light capturing technologies, improved backsheets, or improved interconnectors, which reflect more light on the cell. So basically, if you put 200 watt cells in the module, you can get like 204 watt out of the module due to the enlarged area of the module and the cells collecting the light from the white area around the cells. And corresponding to the cell efficiency increase and the cell to module power ratio, also the module power will increase. And just to give you a value for 2017, typical P-type mono-PERC module should be around 300 watt, and the multi-PERC should be 285 watt. Just if you want to compare data sheets, so that should be state of the art there. All for 60 cell 156 by 156 millimeter. Remember what I said about the wafer sizes earlier. Okay, so some other module issues. Frameless will remain a niche market. Other frames like plastic, so aluminum will stay mainstream as a frame material. Also, these smart junction boxes, which are very popular in the US, in the overall world market, will remain a niche market there. Then module dimensions or cell dimensions. This is an interesting trend. So with a higher currents from the cells due to the smaller finger widths and improved UV and infrared response, more and more people cut their cells in half and to reduce the current and therefore reduce the resistive losses in the module. And so this will become a trend, and the modules will get bigger due to that more and more modules will be installed in big power plants or large commercial systems. For residential, people prefer smaller modules, but as for big power stations, larger modules are much more cost effective. So the trend is to the 72 cell modules. going larger there. Then also a new graph, we asked the participants, what about the warranty? So, and the performance, the product warranty will remain at 10 years, but the product warranty will increase from 25 to 30 years eventually in the next 10 years, so that is foreseen. Also the degradation values are thought to be reduced because the people know their modules better, they can judge the degradation better, or they can label their modules a little higher and take care of this initial degradation. So there you can expect 2% initial degradation and 0.6% as a warranty, I mean, to the customer. So if the module does not fulfill this, you can claim, you can make a warranty claim. I think there's also good news showing people that the product quality is still to increase for PV products, because these are big commercial factors when you build large power plants, of course. Okay, this also brings me to the systems part already. So here we see the balance of system trends for power plants in Europe and the US. It's very similar on the left-hand side, and on the right-hand side in Asia. They're all normalized to 100%. So this does not show that generally in Asia the costs are significantly lower than in Europe and the US. But it shows you the trend, and it shows you that still the modules will, although they make great progress in cost reduction, still be the major part of the PV power plant cost reduction. Basically the fraction still stays about the same, so the modules will still make up 50% of the power plant costs. So this leads then, if we take these numbers and calculate the levelized cost of electricity, so we assume an average system price, let's say in US or Europe at $970 per kilowatt peak. This will lead, depending on the irradiation, so let's say that's northern Europe, maybe 1,500 kilowatt hours. I think maybe that's representative to southern Europe, and the most sunniest regions will get 2,000 kilowatt hours per kilowatt peak, and then you can reach already today levelized cost of electricity, but without all the overhead costs. So this is just the pure system costs, not the administration costs, and interest rates are included, but what you need to pay to the government to get some approvals, these fees vary from region to region. Those are not included. So this is basically the lower boundary of the levelized cost of electricity. But already you can see in Germany, the lowest auction was at 5.7, so already lower. The average in Germany for the last auction for PV power plants was at 7.7 US cents. So it's right there, and the lowest bid we have seen in Abu Dhabi is at 2.47. So this tells you that PV electricity is right there, or very cost competitive in most regions of the world to conventional electricity already. So if you hear people say, yeah, PV is too expensive, then look at the most current numbers, and you have seen the dramatic cost and price reductions, and PV is cost competitive in many areas. And if you increase the lifetime to 30 years, then you can even go down further, because we only assume 25 years. So I'm coming to the end. So here we come back to the learning curve. So if we just look at the last, let's say, 6 years, then one could think that the learning rate increased steeply, but this was due to, let's say, market conditions of undersupply of silicon and modules at that time, because there were the big feed-in tariff increases in Spain and Italy at that time, so the modules were scarce. And still, if you look at it at a differentiated way and only extract the watt peak learning, so what has been done and achieved in cost reduction by increasing the power of the module, it was about 7% per year. And the per piece learning was 26%. So most of that being economy of scale and technology advancements, but also market influenced. So this number and also these data points down here, they are governed by the huge oversupply. So why do the points down here undershoot the long-term learning rate? Because there is not a regular market, but there is a huge oversupply. So, and then we are coming just to the last slide, so how to grow the PV. So spreading PV can be seen like a plant where you seed it and then it's shooting. Then you do some singulation. That's what's happening with the PV industry right now. Then it starts fertilizing and it's growing, it's flowering, and then it finally develops the fruits. So this was an experiment done by Markus Fischer, one of the co-authors of this, and he made this parameter set just to show that there is this S-shaped learning, which you see from many industries, and you can take this to PV, and PV is just down here. So, and this is the scenario we put. This is actually the high scenario, although I think with less than 10% primary energy, it's a low scenario for me. But some people, especially the International Energy Agency, think it's a high scenario. But this will result that we have to at least 5 times or even 10 times increase our production capacities worldwide, which is shown here. And they're still lacking the actual market development. So this brings me to the summary. So I think silicon PV, as I hopefully could show you, will remain a fast-moving technology. Further reductions in manufacturing costs are possible without sacrificing quality and reliability. That's a must. And further cell efficiency improvements will also help with the cost reduction on the system level. And I hope I could show you also silicon PV will significantly contribute to future energy demand, and we are just at the very beginning of the PV market development. Thank you very much.
Thank you very much, Axel. We have class after us, so maybe we can take some questions.
It's outside, yeah.
And Axel will be here also tomorrow, so if there is some question that you cannot get today, we'll do it tomorrow. So let's thank Axel again.
Thank you.